Some solutions for book problems, section 11.2, finding slopes and lengths of polar curves. We're going to do numbers 21 to 27 odd, and then 39 to 44 all. All right, number 21, directions say find the slope of the tangent line to the polar curve for the given value of theta. And for the first one, we've got the curve r equals 2 sine theta. So to find slope, or dy dx, we have to parameterize this. You can write that however you want. My habit is to do y equals r sine theta and x equals r cosine theta. I do them backwards like this because this is the one that's going to end up on the top. And I'm going to use my trig identity knowledge here. You don't have to, but it removes the product rule from the game. That's the same as sine of 2 theta. So dy d theta is equal to, let's see the chain rule on this, that would be 4 sine of theta times the derivative of what's inside is cosine theta. Remember, it's helpful, I think, to write these like this, so you can really see what's happening there with the chain rule. And dx d theta is equal to 2 cosine 2 theta. Again, the chain rule popped a 2 out there. So that means that dy dx is equal to this over this. If you spot it, you could do trig identity there. That's the same as 2 sine of 2 theta over 2 cosine of 2 theta. And then the 2's cancel there. So sine of 2 theta over cosine of 2 theta, and we're doing this at theta equals pi over 6. You can make that tangent if you want to, but we all think in sines and cosines, so maybe I'll just leave it like that. So that's sine of pi over 3 over cosine of pi over 3. The sine of pi over 3 is the square root of 3 over 2, and the cosine of pi over 3 is 1/2. So that slope is the square root of 3. Right. Rightio. Number 23. I'm going to find the slope of r equals 1 over theta at theta equals 2. It's 2 radians. And it's about 110 degrees or so, 115 degrees, if you're just trying to orient yourself. And this is kind of spiral sort of thing, right? It would spiral inward, where the r would get smaller and smaller. If you're thinking polar, what that would look like. Make a quick sketch of it just for fun. So when theta is 0, that's undefined. And oh, it's not quite that at all, is it? And then when theta is, let's say, 1, which is about 60 degrees, then it would be out at 1. When theta is very, very close to 0, it would come in like this from positive infinity, right? And then it would spiral in like this. Something like that. And they get smaller and smaller there as the theta got bigger. Okay, so let's see. So parameterizing this, y would be equal to r times sine theta, and x is equal to r cosine theta. That's the same as sine theta over theta. Write it like that. And that's cosine theta over theta. So the derivatives, dy d theta, using the quotient rule, well, I guess you could make it times theta to the -1 and do the product rule if you want, but go ahead and do the quotient rule. Good to remember these things. So that's low d high minus high and d low, since theta is the variable of choice if you're doing derivatives d theta. The derivative of theta is just 1 over low, and then dx d theta is equal to low d high is negative sine theta minus high d low is 1 again over theta squared. So when I put these over each other, dy dx is equal to this over this. Notice the theta squareds will cancel out. Theta cosine theta minus sine theta over negative theta sine theta minus cosine theta. And plugging 2 in, I get 2 cosine of 2 minus the sine of 2. That's not a nice angle, nothing really we can do about that. And then minus 2 sine of 2 minus the cosine of 2. There might be a little bit of simplifying you could do there if you multiplied by a conjugate or something like that, but I don't think there's any great advantage to be had there. So I wonder what they have. I have my book here. I'll just check real quick, see what they have in the back. 11.2. Well, I opened it to the right page. Let's see if I can find it now. That's number 23. Yeah, they did a little simplifying. It looks like they multiplied the top and the bottom by 1 over the sine of, they divided the top and bottom by sine of 2, it looks like, and then switch the signs around. So, again, I don't think there's a huge, oh no, they divided by cosine, I think. In fact, they divided by negative cosine too. So that's how you get that to look like the answer in the back of the book. But that's fine like that. All right, number 27. Let's see, what do we have here? 27, sorry, that's not the next odd number. 25 is r equals sine of 3 theta, and that's at theta equals pi over 4. We're going to find that. So parameterized, y equals r sine theta. You can't combine those because it's a different argument on the inside. X equals r cosine theta. Taking the derivatives, no getting away from the product rule here. So let's see, the derivative of the first would be 3 cosine 3 theta times the second plus the first times the derivative of the second. Sorry, I'm getting ahead of myself there. That is dy d theta, and dx d theta is equal to the derivative of the first, 3 cosine 3 theta times the second plus the first times the derivative of the second. And now I can turn this into a fraction to find dy dx at theta equals pi over 4. I'm just going to write that all out. So that's 3 times the cosine of 3 pi over 4 times the sine of 3 pi over 4 plus the sine of 3 pi over 4 times the cosine of pi over 4. And then on the bottom I've got 3 cosine 3 pi over 4 times the cosine of 3 pi over 4 minus the sine of 3 pi over 4 times the sine of pi over 4. Okay, let's plug values in carefully into that and see what we can do to simplify it. So I've got 3 times the cosine, that's the x value at 3 pi over 4. That's negative square root of 2 over 2. And then the sine of 3 pi over 4, that's the y value there, so that's positive square root of 2 over 2. Plus, did I make a mistake plugging things in here? That should just be a pi over 4, shouldn't it? And did I do the same thing here? These two should just be pi over 4s. Which won't make a difference for this one, but it would for that one. It would mess up my signs, S-I-G-N. All right, so that's okay. And then the sine of 3 pi over 4 is the square root of 2 over 2, because that's the y value at 135 degrees. And then cosine of pi over 4 is the square root of 2 over 2. And then here, I've got 3 times the cosine of 3 pi over 4 is negative square root of 2 over 2, positive square root of 2 over 2, and then minus, and these are both positive, square root of 2 over 2. All right, let's see. Simplifying that, I have here 3 times 2 negative over 4 plus 2 over 4. You can reduce those, I'll do that next. And then this is the same thing, negative 6 over 4 again, and then minus 2 over 4. So actually it's pretty easy to leave them like this, isn't it? That's negative 6 plus 2 is negative 4, so that'd be negative 1 on the top, and that's negative 2 on the bottom. So that looks like it should come out to be 1/2 if I didn't mess anything up there. Let's just check that. 25 is 1/2. Yay! Just bookmark that page there. Okay, number 27. Let's see what we've got. Here, calculate the slopes of the tangent lines indicated in the accompanying figures. So in 27, we've got a cardioid r equals 2 plus 2 sine theta. I'm going to go ahead and just find the dy dx for this, and then we'll find our other values. We'll find where we're going to plug in, what thetas we need to plug in. So let's see. My y would be equal to r sine theta. X is equal to r cosine theta. And let's see, how much simplifying do we want to do here? I think I'm just going to take the derivatives as they are here using the product rule. We'll see how that goes. So dy d theta is equal to the derivative of the first is 2 cosine theta times the second plus the first times the derivative of the second. Dx d theta is equal to the derivative of the first. It's the same thing that it was a minute ago. 2 cosine theta times the second plus the first times the derivative of the second. So that's good practice for quotient rule. How much do we want to try to simplify these? Let's see. So dy dx. I think we do want to a little bit, at least make an effort, because we're going to be plugging values in. So I've got 2 cosine theta sine theta, and then another one of those 2 sine theta cosine theta when this distributes here. And 2 sine theta cosine theta is the sine double angle. So I've got sine of 2 sine of 2 theta. That's this and this. And then I also have 2 cosine theta. So that's a simplified version of that. Here I've got 2 cosine squared theta minus 2 sine squared theta. Again, you don't have to recognize this, but that's the cosine double angle formula without the 2 in front. So that's the same as 2 cosine of 2 theta. That's equal to that and that. If you didn't recognize that, you can still get the right answer. It's just a little messier, I think, to get there. And then minus 2 sine theta. That has a nice kind of symmetry, too, the way that we wrote it there. Okay, now we just need to figure out for what values of theta. So the cardioid looks like this, and they've got tangent lines drawn in here, here, and here. So it looks like that's at theta is equal to 0, theta is equal to pi over 2, and theta is equal to pi. And you wonder what would happen if you did at theta equals 3 pi over 2. Well, that looks like it has a sharp corner there, doesn't it? So that probably means that here we would get a 0 over 0 condition, right? It's not like it's getting vertical. It looks like it's just getting, or maybe it's something over 0. Maybe it does get close to vertical there and come back. But one way or another, the denominator is going to be equal to 0 there, so they didn't ask us to find that. All right, so let's do those. So at theta equals 0, dy dx is equal to 2 sine of 0. Sorry. Oh dear, that's not a theta, it's a 0. Plus 2 cosine of 0 over 2 cosine of 0 minus 2 sine of 0. Ah, did it again. So the sine of 0 is 0, so those go away. So I got 2 cosine 0, 2 cosine 0. So cosine of 0 is 1, so that's equal to 1. Which, that looks about right, doesn't it? The slope there should be 1. And then I'm just going to say, by symmetry of the curve, dy dx at theta equals pi is equal to -1. Right? I mean, you just kind of tell by looking at that. It's a symmetric thing. So, and certainly it looks like here the slope would be 0. So theta equals pi over 2. We'll just check that real quick. We'd have dy dx is equal to 2 sine of pi plus 2 cosine of pi over 2, right, because that's a 2 theta and that's a theta, and it equals 2 cosine of pi minus 2 sine of pi over 2. So and we expect that this should be 0. So the sine of pi is 0, and the cosine of pi over 2 is 0. Sure enough, just make sure that it's not 0 over 0. 2 cosine of pi is -1, so 1 minus 2 times the sine of pi over 2 is 1. So that's 0, just like it looks. Just make sure that that 1 and, yep, so we're all good there. Okay, so I mean, it's messy to do that, but just have some discipline, be careful. In other words, give a care about what you're doing. What are we doing now? 39. Now we're finding lengths of curves. And I think that really I'm interested in more than anything else. We talked about this in class, I think, you just being able to set them up. So here, the entire circle r equals a. So for all of these, I need to also know dr d theta. So that would just be 0, right? Because that's a constant. So that means the length of the curve, the whole thing. This isn't a sine or cosine circle, it's just a radius equals. So you have to go all the way to 2 pi for that. So it's square root of r squared plus dr d theta squared. So that's, when you simplify that, this one would be very easy to do by hand. The antiderivative of a, which is just a number, would be a theta, because theta is the variable. From 0 to 2 pi, that would be equal to 2 pi times a. And that makes sense because the radius of the circle is a, so the distance around the length of the curve, 2 pi a, it's like 2 pi r. It's the circumference. All right, number 40, the entire circle r equals 2a cosine theta. Now this is a cosine circle, so to get the whole circle, I only need to go from 0 to pi. That's important to know. Dr d theta would be equal to, that's just a constant, so negative 2a sine theta. So r squared is 2a squared times cosine squared theta plus this squared. That squaring is going to remove the negative sign, so I'm just going to ditch that. And there's a cosine squared plus sine squared with the same factor on them, so that would just equal 1. So the whole inside of this would just be equal to 2a quantity squared. When I take the square root of that, that's 2a, 0 to pi. That's easy enough to do by hand, so I'll go ahead and do that. So the antiderivative of 2a is 2a theta, because 2a is just a number. And once again, I get 2a pi, or 2 pi a if you want. And that should also make sense because when we start making this circle, the graph of that, it's a cosine circle, and it's sitting on the x-axis, and it starts right here at 2a. So the radius of the circle is also a. The 2a here, this is the diameter. Cool. Number 41. The entire cardioid r equals a times 1 minus cosine theta. So dr d theta is equal to a, that's just a number, times sine theta. Okay, so the entire cardioid has to go all the way to 2 pi to repeat. So that's a squared times 1 minus cosine theta squared plus a squared times sine squared theta d theta. There's some simplifying that could be done here. So if you FOIL this out, there is going to be a cosine squared times that, and there's the sine squared times that. So there's some simplifying that could be done. You could also just factor right now that a squared could come out to the front, and it's a constant, so it can cross that barrier there. But I'm really interested in just you being able to set that up, so I'm going to leave it there. 42. R equals sine squared of theta over 2. I'm going to write it like this because I'm taking the derivative from theta equals 0 to pi. All right, so taking the derivative, dr d theta is equal to 2 sine of theta over 2 to the first power, that's the power rule, times the derivative of what's inside, cosine of theta over 2, and then again times the derivative of what's inside, because that's not just theta, so times 1/2. So that 1/2 and the 2 cancel, and if you want to, you can recognize that that's your, it's kind of close to your sine double angle, so that's actually 1/2 sine of theta. I'll let you think for a minute about how that works, that trig identity. But there it is, there's your answer. So it's the sine double angle formula. You should spend a minute just making sure you get how that works. You would not have to do this if you're just setting this up, but you never know. So if you had to match up to the right answer, got to be able to recognize that. So I need r squared, so that's sine of theta over 2 to the 4th plus dr d theta squared, and that's 1/4 sine squared theta. And I'm definitely going to leave that like that. Number 43. Let's see. I've got r equals e to the 3 theta. That's an exponential spiral from theta equals 0 to 2. So dr d theta would be equal to 3 e to the 3 theta. So here I've got this squared, an exponent to an exponent, you multiply those, so that's e to the 6 theta, plus this squared would be 9 e to the 6 theta, d theta. I'm going to actually do this one because I think this could be done pretty handily, and we can check it with what the book says. So those are like terms, so I've got 10 of those. So the square root of 10 is just a constant I can bring to the outside. And then the inside, I've got e to the 6 theta, but I've got the square root of that. That's e to the 3 theta. So that's the square root of 10 times the antiderivative of e to the 3 theta is 1/3 e to the 3 theta. I moved the 1/3 out here because it's just a constant. So that's equal to the square root of 10 over 3 times e to the 6th minus e to the 0. So some version of that. And let's see, that's an odd one, so let's check and make sure that we're good there. Square root of 10 times, yep, they left a 3 on the inside, but other than that, that agrees. So that one wasn't bad to do because that actually simplified into something pretty easy to handle. Number 44, last one, r equals the sine of theta over 3 cubed, and we're going to go from 0 to pi over 2. So dr d theta, got a couple levels of chain rule here. Derivative of something cubed is 3 times that thing squared times the derivative of what's inside. It would be cosine of theta over 3 times the derivative of what's inside that is 1/3. So the 1/3, the 3 cancel out. And then just setting this up, I have r squared, that's sine of theta over 3 to the 6th plus dr d theta squared, which would be, let's see, sine of theta over 3 to the 4th times cosine squared of theta over 3. Sorry, that's a little bit inconsistent how I'm writing those. I did that one there and I did that one there, but you know how that works. This one actually can be done too. You could factor out a sine to the fourth from those, which could come to the outside as sine squared, because you're taking the square root of that. And then on the inside, you'd be left with sine squared plus cosine squared of the same thing, so that would turn into a 1. Then you'd have a sine squared on the outside, and you'd have to use a trig substitution to get that. I think that comes from a half angle formula, so that's a messy thing. So I'm happy here if you just get that one set up. Okay.